Hello, I'm Kayla Flager, and today we are going to be taking a look at the electron domain geometries by attaching balloons to one another for a visual representation. Electron domain geometry basically describes the shape that molecules make, the shape that molecules exist in. So electron domains are basically a lone pair or a bond that are connected to the central atom in a molecule. An electron domain can be a lone pair, it can be a single bond, a double bond, a triple bond. It doesn't really matter what it is. It's just the number of electron domains that are connected to the central atom that really matters. According to the VSEPR model, or the valence shell electron pair repulsion model, we know that electron pairs in the valence shell are going to repel one another. So they're going to arrange themselves in a way so that they are as far apart from each other as possible. Depending on how many electron domains are attached to a central atom in the molecule is going to determine how those electrons repel themselves and what shape is going to take place. There are 5 different electron domain geometries that we're going to take a look at today. The first electron domain geometry that we're going to look at is the AB2 model. AB2 is really just a way to describe the type of molecule that we'll be looking at. So A and B obviously are not elements in this case. They're just kind of a way to express a placeholder for specific elements that we could plug into this formula with the two atoms connected to the one central atom. So on our example, the place where the balloons are connected is going to be the central atom, and then the 2 balloons are going to represent the atoms that are connected to that central atom. So with an AB2 model, there are 2 electron domains. An example of this would be BeCl2, or beryllium chloride. This would represent a linear geometry. The atoms are all in a straight line together, and the central atom, which is beryllium in this case, does not have any lone pairs. It's connected by 2 single bonds to the chlorine atoms in this case. The AB3 model represents a central atom that has 3 additional atoms attached to it. There are 3 electron domains in this case. An example of this would be BF3, or boron trifluoride. Boron, which is the central atom, does not have any lone pairs. It's connected to the fluorine atoms with single bonds, and this is an example of trigonal planar geometry. All 3 atoms are repelled equally, so they form a triangular shape, and they are all on the same plane. It's kind of a flat type shape in this case. The AB4 model is where things start to get a little more interesting because there's a little bit more dimension to it. The AB4 model, the central atom is kind of inside of here. You can't really see it too well. And then there are 4 atoms attached to that central atom. An example of this would be CCl4, or carbon tetrachloride. Carbon, which is that central atom, does not have any lone pairs. It's attached to the chlorine atoms with single bonds, and this would be an example of tetrahedral geometry. Next, we have the AB5 model, and in the AB5 model there are 5 electron domains. The central atom, which is kind of behind this gold atom, in between all of the different atoms, would be connected to these 5 different balloons, so or 5 different atoms in this case. So there are 5 electron domains. An example of this would be PCl5, or phosphorus pentachloride. The central atom, which again is right in here, would have 0 lone pairs, and so the phosphorus is connected to the chlorine atoms through single bonds in this case. 5 single bonds equals 5 electron domains. This shape is trigonal bipyramidal. 3 of the atoms in this case, just look at the purple, the green, and the gold balloon, would be in the shape of the trigonal planar geometry. And then the 2 additional atoms are going to point in opposite directions of one another. So that together forms the trigonal bipyramidal geometry. Oops. And last but not least, we have the AB6 model. The AB6 model has 6 electron domains. So you can see this right here is the central atom, and then each of the balloons represents the atoms that are attached to that central atom. An example of this would be SF6, or sulfur hexafluoride. The central atom, in this case sulfur, would have no lone pairs. They would all be connected to the fluorine atoms through single bonds. 6 single bonds equals 6 electron domains. This would be an example of octahedral geometry. So we see the 6 different balloons kind of take shape, in this case, into the octahedral geometry. So this was a really great way to be able to visualize the different electron domain geometries, and I really enjoyed getting a more hands-on approach with it. So thank you.